Also, when a force is applied on an object, it can have an effect on its direction. For example, in football, when the goalkeeper pushes the ball away in order to prevent the team from scoring a goal, the ball will change direction instead of moving into the net. Forces also have an effect on an object's ability to accelerate, so we can increase our speed at a constant rate. An example of this is in running events, particularly sprints, where we need to generate lots of power quickly. So the runner will apply a greater force into the ground, which will produce an action-reaction force of the same amount in order to accelerate the athlete forwards. On the other hand, forces can also cause deceleration, to cause a body or an object to slow down to reduce its velocity. And this can be shown in basketball when the players are dribbling. They can manipulate their dribble by putting less power when pushing the ball towards the floor in order to decelerate the speed of the ball and to allow them to change direction quickly. The last effect that forces have on objects is that when it acts upon an object, it allows them to change shape. For example, when a footballer strikes the ball when taking a penalty, they apply a force on the ball which will change its shape slightly because of the contact point. The small change of shape occurs because it is forced into motion, from suddenly going from a stationary position to being forced to move. Forces are measured in newtons, and they can be measured by force platforms, which help to measure the three components of the ground reaction force: the location of the force application and the free moment of force. Newton's laws of motions are three proposed laws that ultimately propose the foundations of mechanical movement by providing a description of the relationship between an object or body and the forces that are acting upon it in order to produce motion. Firstly, we have Newton's first law. This states that an object or a body which is stationary, or moving in a linear way, will remain at a constant speed unless there is an internal or external force acting upon it, which is known as inertia. The term inertia is used to describe an object's tendency to resist changing of its motion, which can be both stationary and moving bodies, unless unbalanced forces act upon the body in order to change its motion. For example, in sport, for objects which are stationary, like a golf ball on a tee, will only produce motion when an external force acts upon it. So when the golfer hits the ball with the golf club, the golf ball will roll along the grass to the hole. However, it is quite reluctant to change and wants to maintain its constant velocity, but the grass may cause an opposing force of friction, so it in turn decreases the ball's velocity. Another example is in basketball when a shooting guard is taking a shot. In reality, it would seem that there is nothing acting on the object to obstruct its path of motion. But this law states that there are several vital forces which are acting on the object in order to create the angle needed to create the arc into the hoop. Otherwise, without these forces, the ball will continue to move in the current direction. One force that will be acting on the ball is the downwards force of gravity. This is represented by the downwards arrow pointing on the ball. So it is important that the athlete can judge the force of gravity by the weight of the ball in order to know how much force they need to push the ball into the right line of trajectory in order to successfully score a basket. If we look at the moving objects in more detail, in running, an athlete has a force which acts against them. This could be resistance, but the athlete themselves has to generate a force by applying a force to the ground in order to cause acceleration in a forwards direction. This is equal to the opposing force, so the net force is zero. As there is a constant velocity, this means that all the forces are balanced, so there is no change in the velocity. When the forces become unbalanced, this results in the change in velocity when one force is larger than the other. We can see the image here represented by the marble that on a downhill slope, the marble will speed up rolling down the ramp, and therefore it will require less force because the movement of the ramp allows the ball to accelerate at a quicker rate. Whereas when the marble is trying to move up the ramp, because of the resistance and the force acting against it, we need to generate a larger force in order to push the marble up the ramp so it can continue to move. And on a flat surface, the marble will neither slow down or speed up unless we apply a larger force to in order to push it against the opposing force. But on a flat surface, the forces would be balanced. The other two would be unbalanced. Newton's second law states that when an object or body is accelerating, their acceleration is proportional to the force which is causing it to move, and will be accelerating in the direction in which the force is being applied. Breaking this down to understand it, by acceleration being proportional to the force, this means that the overall acceleration is affected by the size of the force. So if an athlete applies a small force on an object, for example a serve in tennis, this will affect the ball's acceleration, making it slower, because there is less force to propel it forwards. Whereas if the tennis player applies much greater force onto the ball, then the ball is going to accelerate at a much faster rate. As acceleration is a vector quantity that has a size and direction, this means that these two quantities can ultimately determine the motion. So the angle in which the player positions themselves and ultimately hits the ball will predetermine its direction of travel. Newton's second law can result in acceleration and deceleration by a net force. So when a player is running in basketball and they're sprinting towards the basket in order to attempt a shot, they will have a resistance force acting against them. And also from contacting the ground will also produce a force to result in a net backward force causing horizontal deceleration, because one force is larger than the other, which therefore creates the motion to slow down or speed up, but it depends on the size of the force. So this law highlights that there is a clear relationship between mass, acceleration and force, and this is represented in the equation as shown on the screen, where force measured in newtons is equal to the mass measured in kilograms multiplied by the acceleration measured in meters per second squared. Another important factor to note is mass. Mass is the amount of substance that makes up an object, which is its total substance. This doesn't change wherever you go and is measured in kilograms. This is all the components in the human body. For example, it makes up our bones, tissues, muscles and organs to make up our substance. Mass is an example of a scalar quantity because it doesn't have a direction, it only has a magnitude. Mass can affect a performer's ability to produce power quickly. So for example, sprinters mainly have a small mass and weightlifters would have a larger mass in order to suit their sports. But if we look at basketball players sprinting for the ball, a player with a lower body mass, even if they apply the same force as someone with a larger mass, will accelerate quicker. So the greater the mass requires a greater amount of force to be generated. So therefore, acceleration is inversely proportional to the mass, as higher mass equals less acceleration. It's just represented by the image here. We can see that the person, in order to make the wagon move and to accelerate, you have to pull and apply force to it. And that's only when there's one object on the trailer. But if there's 4 objects on the trailer, we've then increased its mass. So therefore then this person is going to have to apply a greater force in order to be able to make that trailer move, to pull it and to make it accelerate. And just to visually show the example of the tennis player, we can see that the angle achieved here on the arm will ultimately affect the direction of travel, whereas if the arm of the athlete is down here, it will affect the direction of travel and we won't get that arc that we need in order to go over the net. So it really depends on the angle produced as well as the size and direction. Lastly, we have Newton's third law, and this relates to the idea of action and reaction forces. This law states that when any type of motion is performed, there will always be a reaction force that acts opposite and is equal to that force. So as we can see here in the picture, when this person applies a force on the wall, F1, the forces will always come in pairs. So when you push on the wall will push back against you to apply the force. The same force. The forces are equal. If we look at this in terms of a sporting example, when performing a layup in the jump phase, the basketball player will apply a force through their legs onto the ground in order to generate the force and power needed to accelerate upwards. As they take off the ground, the ground will apply a reaction force back onto the player in order to allow them to accelerate in the opposite direction, in this case in an upwards direction. And we can also look at this in terms of a sprinter as well. So the sprinter is going to have a resistance force acting against them. For example, if it's outside, it's going to be the wind. And And when they're in the blocks, they're going to be applying a reaction force into the ground to generate the power needed in order to accelerate quickly out and sprint out the blocks. So this force applied is going to be equal to the resistance, and then when they apply it, they need to apply greater force then in order to overcome that resistance and sprint out the blocks. So in summary, this law is mainly about reactive forces and how every action and movement there is an equal and opposite reaction force. So now we're going to be looking at stability and what stability is and how it can affect our performance in our sports. When looking at stability, it's important to understand how mass can actually affect how stable we are. And as we mentioned, mass is sort of the substance that makes up our body. So now we have to think of this in terms of centre of mass. And our centre of mass is the point at which our body is balanced in all directions and planes. The centre of mass is normally found in the centre of our body, and gravity acts down through the centre of mass in order to keep us stable. However, this can change in sports to do with our position. As we can see on the screen, we have two very different performers in two very different positions. So first of all, if we look at the gymnast on the beam in the handstand position, we can determine that her centre of mass is going to be further towards her head, so it's further up her torso. And this is going to be in order to allow her to balance on her hands, because the force is being maintained in her hands. So there is the force of gravity is having to act down in order to keep her stable. And because her hands are very close together, it's therefore hard for her to maintain her balance. So the centre of mass has to move up in order to try and keep her stable and in her midline. Whereas if we look at the basketball player, their centre of mass will probably be around their core area, maybe a bit lower, because they have quite a wide stance in order to keep them stable. Because their body weight is more evenly distributed, we can see the difference between the two pictures, how being in a low stance, you've got a lot more control, much wider, evenly distributed, so you're more balanced, whereas a gymnast who's literally relying on her hands in order to balance and is having to focus on the beam with her head is going to have a much less stable position, so therefore the centre of mass has to move in order to accommodate the position. So the centre of mass can move depending on the sport. And it's also to do with reaction forces. So as we've said before, if force is applied through the ground when we're attempting, for example, to jump over the high bar, the centre of mass is going to have to shift as we jump upwards over the bar in order to provide us with the energy and effort to do this and to provide the angular motion. So centre of mass would actually in this case be on the outside of our body, on top of the bar, so in order to encourage the rotation. Whereas when we are, for example, a long jumper is in the execution phase and they're jumping up, the centre of mass is going to move with the athlete as they move upwards in order to keep them balanced and them stable as they enter the piked position. And this just relates to what we've just explained about the centre of mass. We can see that as you change your position, your centre of mass alters in order to accommodate that. So we can see when you're just standing normally and you're about your normal height and standing normally, your centre of mass is in your core. Whereas if you're running, it moves slightly downwards. And when you're in fact trying to achieve a position like a karate player or a gymnast, it's going to move upwards in order to keep you balanced, because obviously your centre of mass has now moved and your line of gravity has shifted. And as we've mentioned about the high jumper, we can see that the centre of mass is around this sort of position in order to accommodate, to allow them to achieve that position to go over. Whereas if we look at this compared to the sprinter, we can see that Usain Bolt, his line of gravity is acting downwards in a straight direction and his centre of mass is his core. So it's allowing him to achieve that position and to remain stable, because when you're sprinting, you're off balance. So you need to have your centre of gravity slightly forwards and allow you to achieve that motion in order to allow you to accelerate forwards. So centre of mass is really important in allowing us to maintain and stay stable.